You are sitting at your desk, fully immersed in a project, when someone taps your shoulder. Hey, got a quick minute? It is the most common, seemingly benign request in the modern workplace. The standard assumption is that your focus works exactly like a tape recorder. You press pause, turn around to answer the question, and then press play to resume your work exactly where you left off. But for autistic, ADHD, or strongly monotropic minds, there is no pause button. That exact same tap on the shoulder triggers acute physical disorientation and an immediate spike in physiological stress. To explain why this happens, the writer Erin developed what she calls tendril theory. When a deeply focused mind locks onto a task, it actively sends out thousands of fibrous thoughts to grip the problem. To switch contexts, that mind actually has to retract those tendrils. It has to reel them back in, one by one. It is a slow, laborious physical process. There is another way to visualize an even more vulnerable state. Imagine your thoughts are not attached to you by muscle, but are instead held on a string. You launch one idea, then another, until you have dozens of live, floating ideas tangled in the air above you. The entire day's working memory is held aloft, kept coherent by a single taut line. That request for a quick minute forces a sudden, jarring change to a complex physical structure. To understand the biology behind this vulnerability, we look to the evolutionary stress framework. The brain functions as a predictive engine, continuously calculating what you are about to need and pre-spending biological resources to meet that exact demand before it arrives. In this framework, a thought, one of those kites, is a high-bandwidth prediction. Keeping it hovering against expected incoming data requires a massive, continuous stream of invisible metabolic effort. Eventually, these hovering thoughts layer and tangle until they snap together. They form stable, automatic rules and habits. They become load-bearing scaffolding. Once that structure is locked in, the biological cost of maintaining it drops to a low, steady hum. A highly generative, fast-associating mind runs a high-overhead, metabolically taxing construction site. Because predicting the future is biologically expensive, the brain strongly prefers the old, efficient scaffolding it has already built. Those established habits have a low risk of failure, and the system knows exactly how much energy they require. If you try to unlearn a deeply entrenched habit or pivot to a massive new cognitive task, you are asking the brain to tear down a load-bearing wall. This is, in every sense, active demolition. The constraint here is metabolic. Your brain provisions specific chemicals for normal, daily maintenance. It does not keep a surplus of the raw materials required for sudden, massive reconstruction. Its regulatory bandwidth is entirely finite. Because reconstruction requires entirely different chemical resources than daily maintenance, a system caught without a pre-allocated surplus hits a wall. To save energy, the brain defaults to the cheapest available path, routing new information around the old structures, patching holes with mental tape rather than funding a full demolition. Rigid reliance on routine reflects a biological system correctly recognizing its current lack of metabolic capital to fund a state transition. But scaffolding is only half the story. There are also the daily kites, the live, negotiating, unfinished ideas floating in the working memory that haven't solidified into anything permanent yet. This active configuration is highly fragile. It is a dynamic state that exists only as long as intense, ongoing focus maintains it. This is a chart showing productivity recovery time following a major interruption. Office studies estimate that an interrupted task takes twice as long to complete and produces twice as many errors. Once derailed, a person requires roughly 23 minutes of recovery time to climb back to their previous level of work. By measuring pupil dilation, a reliable biological indicator of cognitive effort, researchers found that the absolute worst time to interrupt someone is at their peak memory load, right when the maximum number of kites are in the air. Because nothing inert was holding those thoughts in place, removing the effort means the entire working set instantly dissipates. The string snaps and the kites blow away on the wind. The neurodivergent thinker cannot pick up where they left off. There is no where they left off. The work is gone, and they have to pay the full metabolic price to rebuild the entire structure from scratch. A plea for transition time, or a do not disturb sign, functions as an accurate report on the absolute limits of a biological system. Every cognitive architecture pays a price somewhere. We see this trade-off in other human capacities. Operating with deep, continuous empathy drains massive amounts of emotional energy. Maintaining hypervigilance or extreme steadiness under pressure physically exhausts the body. We do not ask a deeply empathetic person why feeling costs them so much. We recognize that exhaustion as the necessary toll for a valuable capacity. A mind that builds fast, layers intensely, and tethers dozens of floating concepts together is performing high-fidelity cognitive work. The massive biological cost of flying those kites is simply the required shape of what it allows those minds to see.